All right, last section before we take a little assessment, but this is 6.4, and this is exponential growth and decay. So with exponential growth and decay, you can imagine we are going to be dealing with exponential functions. They are going to have an exponent in it. And what exponential growth and decay is just simply the growth of something or the decay of something that on my x-axis I would have time. So something that is increasing or is decreasing over this time on my x-axis. That's what we're talking about. So a quick definition. Exponential growth occurs when a quantity increases by the same factor over equal intervals of time. Exponential growth occurs when a quantity increases by the same factor over equal intervals of time. It's going to have some sort of common ratio, some sort of growth factor, something that you're going to multiply by. And here's your exponential growth function. Yes, commit this to memory. Y is equal to A times 1 plus R raised to the T power. And you can see the similarities to our exponential function as y is equal to ab to the x. A, b. Remember, when we were looking for our constant ratio, we took what was in these parentheses, and that is what we multiplied by once we got our y-intercept. And you're raising it to some power. This y, this is the final amount that we're going to end up with. It could be anything that grows exponentially. Bacteria, money. A is your initial amount. In parentheses here, this whole thing, this 1 plus R, this is your growth factor. This R specifically is your rate of growth. That is going to be in a decimal, because it's usually going to be given as a percentage, and we're going to have to change that into a decimal. This T is our time for how long it's going. So you have a final amount, which is your initial amount, multiplied your growth factor, which is 1, plus the percentage in a decimal of the growth rate raised to the T power to the time. So here we go. Here's an example problem of how we use it. Really, what you are just going to do is use this formula to solve some problems and answer some questions. So here's a situation. I have an inaugural attendance. Inaugural attendance at a music festival. Seems far-fetched these days, but let's say when all this opens up, somebody's going to be like, we need to get back to normal. I'm going to put on a music festival. The inaugural music festival is the first one that they do. So the inaugural attendance at a music festival is 150,000 people. They expect the attendance to increase by 8% each year. So let's just set the scene again. You're making a music festival, expect 150,000 people at the first one, and then you expect that to grow 8% every year. And what this function lets us do is let us figure out what the attendance is going to be after so many years. You got to take into consideration with the exponential growth, you're going to take that initial 150,000, then you're going to multiply it by the 8%. And the next year, you're going to take whatever that number is, multiply it by 8%, take that product, multiply it by 8%, and it just keeps getting bigger and bigger and bigger. Here's our directions. Write an exponential function that represents attendance after T years. And that would be very advantageous to have something where I had all of these filled in, and then depending on how much time had passed, I could figure out after how many years what my attendance would be. It will be very usable once I have that. If it is increasing by 8% each year, it's going up, we're definitely going to use growth. Your final amount is equal to your initial amount times 1 plus the rate raised to the t power. Well, your final amount is going to be your initial amount of people, 150,000, times 1 plus my rate, which is 8%, which in a decimal is 0.08, and that's raised to the t years. All I have to do now to simplify this is take that 150,000, put this as 1.08, and raise it to the t power. This function right here will now tell me the attendance after how many years with an 8% growth per year. So what that allows us to do is I could say how many people attend in the 5th year. So I'm just going to take and plug in what I know. The amount is going to be 150,000 times my 1.08 raised to the t power. Now you got to be careful here. In the 5th year, remember, in the first year, there were 150,000, 2, 3, 4, 5. So that the amount of time since then is not going to be 5. It is going to be 4. That's what I got to put into my calculator. That's what I got to figure out. I would put in 1.08 raised to the fourth power following order of operations, hit enter, times it by 150,000. Remember, your calculator will do this. I can take 1.08, raise it to the fourth power, I get a number, and I can times that by 150,000, and it gives me that number right there. I will just go to the nearest person. 204,073 people after the 5th year. In the 5th year, that's how many I would expect to attend. That's growth. On the flip side of that, we've got decay. And that's something that's just going to be decreasing by the same factor over equal intervals of time. So when a quantity decreases by the same factor when it decreases by the same factor over equal intervals of time. Should probably label this as exponential decay. It's going to look very familiar to what we just did. And hopefully you can see the difference right here. Now this growth factor, instead of adding the rate to it, I'm just going to subtract it from it. Everything is going to stay the same. This is going to be your final amount. The A is initial amount. This whole thing together in parentheses, this is not our growth factor, this is our decay factor. And again, if I think back y equals AB to the x, this is what it's going down by. And of course, it's going to be less than 1. It's going to be a fraction because you're going to take 1, subtract something, that rate. It's going to go down. This R is still, just like the first one, is your rate of decay now. It's not growth, it's your rate of decay, but it will still be a decimal. It's going to be a percentage that we're going to have to change into a decimal. And your T, of course, is going to be your time. Few parameters on this though. We want A to be greater than 0. I'm not going to start with 0 as my initial amount because this whole thing, no matter what T is, no matter what R is, once I multiply it by 0, that will be 0. And this R, because it will be a fraction, which we already said, that R is going to be between 0 and 1. It's going to be a percentage switched into a decimal. That's it. Let's look at some data. I'll throw some data in a couple of XY tables here. Question is, it growth or decay, and kind of by how much? What's that R factor? Hopefully you can see. as x is going up, if this was time, my y's are going down, and this is going down by 3. This is absolutely decay over here. And you can see that it's going down, and it's decay by 1/3. It's decreasing by 33%. Each time it's going down by 1/3. This is going up 5, 10, 20, 40, 5 times 2, 10 times 2, 20 times 2. This is absolutely growth. And it's growth by 2. It's doubling. It's doubling. We just want to be able to look at it and make sure that we know. Now be careful on these, because I could throw one in there that's linear, that's going to have a constant rate of change. But again, we're going back to that idea of a ratio. With exponentials, you're going to have that common ratio. It will be division or it will be multiplication. It is not going to be addition or subtraction like with our common difference in our rate of change. Again, we're going to ask, is this growth or decay? This time, though, we are going to identify the percent rate of change. So here we go. There's A. Now, when I'm presented with these two equations, hopefully you can see the difference right now and can just make the determination whether it's growth or it's decay, because this is 1 plus something. This is growing at 7%. That 7.07 came from the 1 plus R. R is 0.07, and 0.07 in a percentage is 7%. As soon as I see this is bigger than 1, I know it's growth. When this is less than 1, I know it's decay. So this is growth for sure, because that is bigger than 1. And the rate of change, well, it's going up by that 0.07, it's 7%. It's 7% growth. On this one, we know it's decay because that is less than 1. So I know it's decay. And to get your rate of change, well, you just got to get from 0.98 to 100. That would give you 0.02. Your rate of change in this one is 2%, because that 2% would take you to 100. 0.02 would take you to 1. 98% plus 2% would take you to 100%. That is all we need to do these problems. Like I said, straightforward. Give these problems a whirl.